All right, hello. Welcome to my channel. This channel's for educationally interested and especially people who want to learn about uh, new and exciting theories of everything, uh, particularly obscure things that you probably wouldn't know otherwise. If this channel didn't exist, then you probably wouldn't know. Uh, and one of them is the reciprocal system of theory from Mr. Dewey B. Larson. Today is video number 218 on the reciprocal system. And I love the reciprocal system because it puts power back into your hands. You can do science, you can do liberal arts uh, yourself. You do not have to rely upon uh, the experts in the white lab coats or the tweed jackets to tell you, how things work. You can just take Larson's simple rules and apply them yourself and, figure out how the world is put together and how it makes sense. And, in general, the scientists, they know the equations. They can usually get the right answers, but they don't know how or why. They don't know what the equations actually mean. They know they work, but they don't know what they mean. They were arrived at, algebraically or otherwise mathematically, whereas Larson's theories and equations are arrived at theoretically. So he understands what the equations actually mean, and that counts for something. So today we're looking at his 1979 book called Nothing But Motion. And Nothing But Motion is something that kind of sums up his theory in general. Larson believed that we live in a universe of motion. The universe is not made out of matter, it's not made out of energy, but it is made out of motion. And motion, for Larson, was the relationship between space and time. It sets up a generalized reciprocal relationship between space and time. Uh, Basically, motion is a fraction with space or time as the numerator and time or space as the denominator. The best example of that is speed. I was running at 10 miles per hour. 10 miles of space in 1 hour of time, space over time. Now we could say, if we wanted to double the speed, we could say, I was running at 20 miles per hour. That's pretty fast. I was running at 20 miles per hour. Or, equivalently, we could say, I was running 10 miles per half hour. So you can either multiply the space or you can divide the time. Either way gives you the same result. That shows a reciprocal relationship between space and time as far as speed goes. But speed isn't the only thing that you can, isn't the only kind of motion. In fact, energy and matter are also two kinds of motion. Energy is actually the inverse of speed, where speed is space over time, energy is time over space. It took me 1 hour to move that thing 20 feet. It's 1 hour of time, 20 feet of space, and that is energy. Matter is actually time to the third power over space to the third power. So that complicates things a bit because it shows that both time and space can come in multiple dimensions, 3 or more dimensions. Larson calls that the coordinate aspects of time and space. Time and space generally have the same qualities because they are reciprocals of each other, just like 3 and 1/3 are reciprocals of each other. They have the same quality, 3. But one has the 3 in the numerator and one has the 3 in the denominator. Um, and so coordinate time and coordinate space. We recognize coordinate space, 3 dimensions, 3 or more dimensions of space, XYZ coordinates or WXYZ coordinates in like Buckminster Fuller 4D. And, we're comfortable with that. We live in that world. But then there is also coordinate time, 3 or more dimensions of time. And that is something that legacy science hasn't, accepted at this point. But it's a natural result from the reciprocal relationship between space and time. The other quality that space and time both have is they are both in scalar clock aspect. Clock time, that's something that we recognize. The clock is always getting later and later and later, but in no particular direction. So that is the flow of time or the progression of time. But there is also, by the reciprocal relation, there is also clock space. Space is always getting farther and farther and farther apart. And you can see that. You can visualize that using a balloon and a magic marker. Put a bunch of dots on the balloon. You blow up the balloon, all of the dots are moving away from each other, but in no particular direction. You suck in the balloon, all the dots are moving toward each other. The further away they are, the faster they're moving toward each other. These are scalar motions or clock space. And you can also use something like raisin bread to envision this. All of the raisins, as you bake the bread, all of the raisins are moving away from each other. Or you can gaze through the Hubble telescope and notice that all of the distant galaxies are moving away from each other. And the farther away they are, the faster they're moving away from each other. And so these are all the progression or the flow of space. Then in addition to that, space and time both have their discrete aspects, meaning that they come in small chunks. They do not come continuously. There is a minimum chunk of space and a minimum chunk of time. And they're very small, so you can't really, resolve one from the other without the most sensitive equipment. But they do have their chunk aspect, not continuous. And one chunk of space in one chunk of time, recall space over time is speed. One chunk of space in one chunk of time is the speed of light. So the speed of light is basically 1 in Larson's system, 1 unit of space in 1 unit of time. And Larson says that speed of light is the midpoint of the universe. So this is the difference between Larson and Einstein, or one of the many differences, where Einstein says that the speed of light is the maximum speed of the universe. Larson says that the speed of light is the midpoint of the universe, and that half of the universe is moving slower than the speed of light. That is the half that we recognize, that Einstein recognized. And Larson calls that the material sector. And then there is half of the universe that's actually moving faster than the speed of light, and that's the half of the universe that Einstein didn't know about. And Larson calls that the cosmic sector. And you can see the relationship between the material sector and the cosmic sector. We know things about the material sector because that is where we observe and we make our measurements. And this is where science has, expounded their theories. Um, but we don't know really anything about the cosmic sector. It's basically invisible to us, even though it's right there, right in front of us. And but with Larson's system, because of the reciprocal nature of it, we can extrapolate knowledge from the material sector to the cosmic sector, because what goes on in the cosmic sector is exactly the same, as far as the generalized picture, macro picture, uh, is exactly the same as what's going on in the material sector, except that you reverse the roles of space and time. Easily can be seen in the material sector. We recognize coordinate, space, and clock time, three or more dimensions of time and a flowing, three or more dimensions of space and flowing time. But in the cosmic sector, we have coordinate time and clock space, three or more dimensions of time and flowing or progressing space. Okay, now this book here, Nothing But Motion, is primarily on atomic physics. And so this is trying to figure out what's going on within the atom. And within the atom, you're talking about what Larson calls the time region and the space region. The time region is within the material sector, the slower than the speed of light sector, where we have coordinate space. But when you go less than 1 unit of space, you don't have space anymore, because space comes only in discrete units. So if you're dealing with less than a unit of space, you are in a world of time. And so that is a subset of the material sector that Larson refers to as the time region. And that is the realm of atomic physics. And then over on in the cosmic sector, again, you have the roles reversed of space and time. And within a unit of time, you do not have time, because time only comes in chunks. So less than one chunk of time is a world of space. So this is what Larson calls the space region. And this is where cosmic atomic physics occurs, or as legacy scientists would call it, they would call it antimatter. Okay, so Larson in this book develops some of the basic rules of atomic physics. An atom is a combination of many different kinds of motion. Within an atom, you always have two photons. These photons are simple harmonic motions, waves. And Larson says they come from a combination of a translational motion and a vibrational motion 90 degrees apart. And the combination of those creates a sine wave. Some of Larson's followers have disagreed, and they say that it comes from a birotation, a combination of two rotations. Either way, it's a combination of two different kinds of motion. And then once you have those two photons, then when you rotate them in two different dimensions, independent dimensions, that creates an atom. And then a third rotation, which Larson calls electric or one-dimensional rotation, then creates kind of the gaps between all of the noble gases. So that has more to do with electric valence. And that's actually what he's talking about in this chapter, which is called simple compounds. And he talks about the various different, so a compound is a molecule, a kind of a combination of atoms. So an atom is a combination of many different kinds of motion, and a compound is a combination of many different kinds of atoms. And in this chapter, he's talking mainly about simple compounds. The next chapter is on complex compounds. And we'll just read a few paragraphs here to give you a feel of where Larson is going. Don't worry, don't fret if you don't really get it, because we're picking up in the middle of a chapter, and this is somewhat difficult stuff. Again, this is this is really organic chemistry, I guess, or chemistry, and he basically sets up rules that are quite different than what you would get from your normal chemistry class. And there's different forms of bonding of different atoms, not only based on their electric valence, but also on their magnetic valence. And I think that's where he's going right here. Okay, here's Larson in his own words for at least a few paragraphs. There is also an alternate type of interatomic orientation that gives rise to what we may call second-order valences. As has been emphasized in the previous discussion, an equilibrium between positive and negative rotational displacements can take place only where the net resultant is zero, or the equivalent of zero, because any value of the space-time ratio other than unity, or zero displacement, constitutes motion and makes fixed equilibrium positions impossible. So, when you're bonding, you cannot do so in a condition of motion. When you're trying to establish simple compounds, you need a fixed equilibrium. In the most probable condition, the initial value from which each rotation extends is the same 0 point, or, where the nature of the orientation requires different 0 points, the closest combination that is possible under the circumstances. This arrangement, the basis of the first-order valences, is clearly the most probable, but it is not the only possibility. Inasmuch as the separation between the natural 0 points, or unit speed levels, is 2 linear units, or 8 three-dimensional units, it is possible to establish an equilibrium in which the initial level of the positive rotation, the positive 0, is separated from the initial level of the negative rotation, or the negative 0, by 2 linear units. The effect of this separation on the valence is illustrated here in figure 2. So in figure A here, you got v on one side and V on the other side. Then in figure 2, you have V and then you have 2. And then on the other side, you have V plus 2. And then on the other side, you have V in number C. You have V on one side and then 2 on the other side, along with V minus 2. The basis of the first order valences is shown in A. Here, the normal positive valence V balances an equal negative valence V at an equilibrium point represented by the double line. In B, the initial level of the positive rotation has been offset to the next 0 point, 2 units distant from the point of equilibrium. These 2 units, being on the positive side of the equilibrium point, add to the effective positive displacement, and the positive valence therefore increases to V plus 2. That is, V plus 2 negative valence units are counterbalanced. In C, it is the initial level of the negative rotation that has been offset from the point of equilibrium. Here, the 2 intervening units add to the effective negative displacement, and the positive valence decreases to V minus 2, as the V units of positive displacement are now able to balance only V minus 2 negative valence units. By reason of the availability of the 0 point modifications illustrated in figure 2b, each of the positive first order valences corresponds to a second order valence, an enhanced valence, as we will call it, that is 2 units greater in the case of the direct valences, x plus 2, and 2 units less for the inverse valences, 8 minus the quantity x plus 2 equals 6 minus x. Compounds based on enhanced normal valences are relatively uncommon, as the normal valence itself has a high degree of probability, and the enhanced valence is not only inherently less probable, but also has a higher effective displacement in any specific application, which decreases the relative probability still further. The probability factors are more favorable for the enhanced neutral valence, as in this case, the effective displacement is less than that of the corresponding first-order valences. The compounds of this type are therefore more numerous, and they include such well-known substances as sodium, no, sulfur dioxide and potassium chloride. An interest, or that is PCl3. Although it looks like it says PCI3, but I believe it's PCl3. An interesting application of this valence is found in ozone, which is an oxide of oxygen analogous to sulfur dioxide. Okay, now it doesn't look like, looks like we should stop right there. Don't get discouraged if you don't really understand this. I think we're just going to trudge ahead here tomorrow, try to get to the end of this chapter, and I think we're going to end up skipping the last 3 or 4 chapters of this book, which go further into organic chemistry, and we're just kind of into the weeds here. It's all pretty difficult stuff, and we're going to try to move into some different subjects. I mean, we're going to stay with the reciprocal system, but we're going to look at some of the other authors who have written on this topic, along with maybe some of Larson's other stuff. You know, hang in there. Don't be discouraged if you don't get it. You'll get it eventually, and have a great day. Talk to you tomorrow.